All right, so now we move into lesson 27, which is waves in two dimensions. And it kicks off by going into this idea of a wavefront diagram, or this idea of how do we represent crests and troughs just in a slightly different way. And then we're just going to add some more terminology and some more structure to waves and wave patterns. Now, first and foremost, we're going to look at this idea of what is a wavefront diagram. Now, wavefront diagrams are constructed of crests, which are these solid lines, and troughs, which are these areas in between, or specifically the troughs would be exactly kind of in that like direct middle space of this white space where it's the high points and the low points, or the positive amplitude and the negative amplitude. The other thing they indicate on here in the wavefront diagram is direction of motion. So if we looked at this wave, we would say, oh, this wave is heading to the right based on this orientation. Or if this was a top-down view from this, we could say, oh, this is a wave that is traveling maybe like forward or whatever else we want to say. But specifically, when we have these wavefront diagrams, they're going to have an arrow on the side that represents the direction of motion. The other thing they mention here is the wavelengths, or the lambda. We know that crest to crest or even trough to trough represent a wavelength. So I'm going to even go from like here to here, or trough to trough. And I'm going to also indicate that as one lambda or one wavelength. Now, there's an infinite amount of combinations of different wavelengths, but again, the most obvious ones tend to be crest to crest or trough to trough. Now, a wave ray diagram is just this idea of we have some sort of logic or some sort of representation of a wave that is heading towards some sort of boundary. And you're going to see what that means in a second, but just generally, if we have a wave and it's heading in a specific direction, we can boil it down to simply just some sort of vector arrow representing that directional motion of the wave. Okay, now when we go down to this idea of reflection, reflection is one of these pieces of terminology we're going to introduce today, which is this idea of what happens if we have some sort of wave, it bounces off a reflecting surface, or what I often like to call this is the boundary. So I would make sure you write this in your notes as we could also call the reflecting surface the boundary, just as a way to like kind of talk about how waves can be contained and how they can reflect off of different surfaces. So reflecting surface or boundary. We take an incident wave, which is this sequence of crests and troughs, again, where there's the lines representing crests, and then there's the middle space representing those troughs. So we'd be like crest, trough, crest, like this. And then the direction of motion is indicated by the angle. Now, incident wave, we can phrase this as, again, saying rather than incident, we can even say like that this would be considered the initial wave, or that initial wave energy that's heading towards this boundary reflecting surface. Now, as it bounces off, it sends a reflected wave, but because in this case, we're going to assume that this is in the same medium, what we're going to do is say that this represents a wave with the same energy, same wavelength, just reflecting the other wave. Now, you could always say that, oh, if this was to change mediums, something else would happen, or some sort of other properties would be introduced, like a shorter wavelength, a slower speed. But for this case scenario, we're going to say that when it's reflected from the incident or initial wave, getting bounced off the boundary reflecting surface, it's going to reflect in this way. Now, the example that they use in the notes here is that they say, suppose that we had like some sort of basketball, and a basketball was up here, and you do some sort of crossover off of the hardwood and it goes to your other hand per se. Let's even phrase it that way. So the ball bounces and then it bounces off the floor and heads this way. Well, we could represent this as the basketball has done some sort of crossover, maybe from your left hand to your right hand or your right to your left, and that incident ray is going to be equal to the reflected wave, and we're going to see that this would have that same wave in terms of the crests and troughs and the overall pattern. We get an initial and a reflected. Now, where this takes us is we want to introduce this idea of when we have the initial wave or the incident wave and it reflects off of a surface, then it creates this unique property that if this is in the same medium, meaning the boundary is just some sort of wall or some sort of reflected piece, and we look at this and the wave will hit off that boundary and then reflect, if this is the same medium, we can then say we have this initial angle, or the incidence angle is equal to the reflected angle. And this is all due to the symmetry that the normal creates and that staying in the same medium creates. So when we say normal from our previous units, the normal force was always perpendicular to the surface. So if this was an object that was on an incline, we could have like this, and then the mass was on the incline. When we said the normal force, it was always perpendicular, or the Fn was always at a 90-degree angle to that given incline. no different than this. When we look at the surface, we draw that invisible. And the number one thing to write here, or number one thing to highlight, I would say, is this imaginary line called the normal line is perpendicular to the boundary. It's not that it's actually there or that it represents any sort of energy in this system. It's just if we have the surface and we know that there's some sort of initial or incident wave going and being reflected, then there's this symmetry created by this perpendicular normal. Okay, and then the law that this revolves around says the following. The law of reflection, the angle of incidence equals the angle of reflection. So this will give us a really nice ability to solve problems where we'll have some sort of initial condition, and then maybe it bounces off one surface or two surfaces, or maybe even three, maybe even four. There could be an infinite amount of surfaces it bounces off of. We should be able to solve at a specific point what is either the angle of incidence or even the angle of reflection. And then sometimes they even ask for the angle down here. So I won't even rule that out between the surface and the wave ray, as it's called. Now, let's go down and do example 1 here. So as a quick read through, a wave is an incident, or a wave is heading towards boundary A, and it reflects off and then goes to B, and then it reflects off B and goes out. What is the angle of reflection at boundary B? And so when we look at this here, what we're going to have to do is realize that we're going to have to bring in some math 10C/20-1 skills just to help us out here, mainly 10C. So what I'm going to do first and foremost is I'm going to draw the reflected rays off of these. So if this was 50, then I'm going to try my very best to match that as it goes to B. And then from B, it's going to get reflected. And by symmetry, it would head off somewhere here. So just to help us out here, I'm even going to throw in some arrows here representing the direction of motion of this. The other thing I would highly recommend is if that normal line is not written in there, just take a second to put a dotted line down the middle perpendicular to the surface to help you out. Now, we're going to use a couple properties here. One, that any sort of 90-degree angle is a right angle. So if we know that that's the case, we can actually solve for this one quite easily because we can say if this is 90 and this is 50, then this must be 40 down here. So we're going to fill that in first and foremost. Here's 40. And then because of symmetry of this idea that it's staying in the same medium, we can say this is 40, which means that this is 50 here. Now, let's provide some specific terminology or some specific outlines for this. So we look at this and be like theta I of A, or the initial angle, the incidence angle of A, the reflected angle of A, or theta, I'm going to call it RA. The reflected angle at A is the 50 degrees as well. And now our job is to figure out, first and foremost, like our end goal we really want to find is this one here, the reflected angle from B. But first and foremost, now we have to use triangle sum theory in order to get this angle here. So using triangle sum theory, and I'm going to put a sigma symbol here just to represent the sum, triangle sum theory, it says that all interior angles sum to 180. So the sum that represents this 180 degrees is equal to 40 degrees plus 110 degrees plus the theta IB, or the incident angle at B, which is going to be that first angle we're looking for. And actually, this isn't even that theta B. I should take this back here and just be like, it's that angle we're pointing to, that missing angle that is contained here. Now, when we do this math, we go 40 plus 110, and maybe I'll just put like an unknown theta here to help us out here. So this theta is going to be equal to 180 minus 40 plus 110 is 150. So this means that angle that's between the wave ray and the surface B is going to be 30 degrees here. So we could fill this in as this is 30. That means this by symmetry is 30. Now the easy thing for us to do is figure out what is the angle of incidence at B and what is the angle of reflection. Specifically, we want to figure out the angle of reflection, but if we know one, we actually know both of them. I'm going to use an arrow to point to this. So maybe I'll do this in green here to get this angle and also to get this angle. Maybe I'll double arrow it there. Both these angles are contained the same way. We're going to do this as 90 degrees minus 30 degrees, which will equal 60 degrees. Now, what is this? This is not only the angle of incidence at B being 60 degrees, but it is also the angle of reflection at B, which is 60 degrees. So our answer that they're searching for would be angle of reflection at B is 60 degrees. Now, you're clearly seeing how a lot of this can be done using mental math. However, you want to be as clear as possible, and so make sure that you're using the idea that right angles add up to 90, triangle sum theory or the interior angles of a triangle all should add up to 180. And then if you can write out as much as you can just to make sure you're for sure getting the correct answer, that would always be a good idea. So this is one of those properties where we have wave ray diagrams, which is simply, and I should even go back to this page here, or go back to the first page. Our wave ray diagram in comparison to our wavefront had these series of line, white space, with an arrow to represent its motion. Wave ray diagram is simply just the vectorial direction of that given wave heading in a specific direction here. All right, now let's flip over to what refraction is. Refraction is this idea that what happens if we have a wave that changes medium. So rather than just being reflected off a boundary, or rather than going from an incidence to a reflection where it maintains that same wave, what we're going to look at is the following. If we have a wave that goes from one medium to another, or a wave that enters a region which is different, such as deep water, shallow water, or vice versa, what we're going to see is that the speed and wavelength will change, but the frequency remains unchanged. And this is the note you got to make here. Right away, when they say the frequency remains unchanged, I'm just going to make like a little subnote by pointing an arrow to this and say frequency, and I've said this a bunch in the unit, including in the lesson 26, frequency is something determined by source. There we go. Frequency is determined by source, which is when we talk about the frequency being determined by source, the thing that creates the wave or creates that wave energy is the thing that is determining what overall frequency we have. The medium can only control the speed and the wavelength because it describes or controls the impedance of the motion of the wave, meaning the resistance to the motion of the wave throughout its medium. So if we're looking at something like maybe we're going from air to water or vice versa, the more dense medium is going to cause the object to have this slower speed through it, or it's going to be more condensed. When we look at the opposite case, we'll see that it is faster. And in the example that we're going to deal with here, we're going to talk about this shallow to deep water, or even vice versa. Depending on the order we look at, which will be below, it's going to impact what the overall speed and wavelength look like in that given region. But again, frequency is determined by source, and this gives us a really nice property that we can work with. So when we look at this change in medium, or this change from one region to a next, medium or region, you can use those interchangeably. We're going to bring back this equation that we established in lesson 26, which is the universal wave equation. And I'm just going to make sure we write that in here just because it is pretty critical. So universal wave equation. And this equation relates speed, wavelength, and the frequency for any sort of wave. And so one thing we can say is that whether it be electromagnetic waves or whether this be mechanical waves, such as the transverse or longitudinal waves, both of these apply to this equation, hence that idea of it being universal. Now, this introduces a nice property because what we can do is say, maybe let's go from one medium to another, or one region to another. I'm going to call this down below. So suppose that we deal with two different regions or mediums. I'm going to have everything denoted by the subscript 1 as medium 1. Everything's denoted by subscript 2, I'm going to have as medium 2. So we're moving from one material to the next, or one region to the next, or one medium to the other. By rearranging these equations, what we can do is we can solve them both so that they're both in terms of frequency. And when we do that, we're essentially dividing by the lambda on both of these independent formulas. When we do that, because we know that the frequency is equal for both of these situations, or even though we've changed regions or the medium, the frequency remains the same, it allows us to create an equality between these two equations, which helps us solve for, if we know that this ratio must be maintained or that the frequency must be the same, then therefore we could solve for some variable or solve for some component of one of the waves, whether it be the speed or the wavelength, given that we know information about the other region. Now, on your formula sheet, this is what you're going to be given here. So you're going to be given the system where they say, rather than you having this as the equation where it would naturally be, where frequency equals frequency, they just rearrange it a little bit here and give us speed 1 over speed 2 equals lambda 1, or wavelength 1 over lambda 2. And this is the one that you're going to work with in order to solve using this equation, we have to have three parts or three pieces of information in order to solve for this. So we have three, and I'll phrase it this way, three knowns with one unknown. Because if there's four variables, then it doesn't work if we, and I'm just going to take out that S there. There we go. Three knowns, one unknown. Because if we didn't know two things and we knew two things, then that doesn't work for this situation. So when we get to our example where we'll actually see this, it's going to be very important we look at this critically, being like, we're going to know three pieces of information, which makes our job very easy. We can cross multiply and divide to get the one variable we need isolated. Now, just as a little bit of a subnote here, when we talk about this change in mediums, this is brought up a lot more in the physics 30 level, and we actually start dealing with the law of refraction, or Snell's law, which is studied in detail at the physics 30 level. For us, we basically just need to use this equation very roughly, but even on your formula sheet, what you're going to see is that this equation actually has one more piece. It's n2 over n1 is equal to this v1 over v2, which is equal to lambda 1 over lambda 2. These are the indexes of the medium, but we don't really deal with that at our level. So don't be worried about this. Like maybe you could even put this into your notes realistically so that you know that this is on your formula sheet in this way. Index 1 over index 2, or I should say index 2 over index 1 is equal to this. But we don't go into that side for physics 20. You will go into that for physics 30. Okay, now continuing this idea of frequency remaining the same, but our wavelength and our speed changing, let's look at the example that was brought up from before. So we want to look at the situation where we have a wavefront diagram. Again, we know it's a wavefront diagram because it has these lines representing the crests, and then it has the open space representing the troughs or the low points. And then what we're going to look at here is that we have a wave that is traveling from high speed to then low speed. And we know it's that direction because the arrow on the front of the wavefront diagram here, this has the direction of the motion. So again, just always be looking for that arrow because it determines the direction of motion. Now, if we know we have a high wavelength and a high speed, this is where we deem it to be the deep region. So this would be the area that the water is deep. So I'm going to put a bracket here and say that this represents our deep water. And I can create a parallel here from lesson 26. When we talk about a large amount of energy is going to have the majority of the ability to transmit that energy from part to part. So if we were thinking about this in deep water, we could think about this as some sort of tsunami. And a tsunami at its origin has a ton of energy and it's moving with a very high speed and it's covering a lot of distance with that high speed. And so we look at this and be like, the crests are going to be spaced out, the troughs are going to be very spaced out, representing that high wavelength, and it also has that high speed. Whereas when we go into the shallow region, which is this other piece over here, so I'm going to put that same curly bracket here representing the different region. This is going to be our shallow region. Shallow regions have or shallow water is, I should say, but we could call it a region if we wanted to. The shallow water has lower energy, meaning it's going to have lower speed, lower wavelength, or there's not going to be as much being transmitted per given unit of time here. So this is a prime example of what a possible wavefront diagram could look like when we go from one medium to the next. And we can kind of directly see that crossover here. This is where our last crest is for our deep water, and then we go into the shallow water from that point. So this is almost like our change point. I'm just going to short form it as change point, but this is where we start to see that difference in region, or what we could say for this unit, a difference in medium is at that point when we start to see that difference in wavelength happen after that key interval. All right, now let's look at an applied example of what this might look like in terms of using this identity from our formula sheet. So a wave travels from a region with a speed of 45 meters per second into a region with 60 meters per second. So it's going from a slow region to a fast region, just based on the context. So what I'm going to do is I'm going to write this as, this is my speed 1, this is my speed 2, just by the order in which things are happening. If the wavelength is 1.5 meters in the slow region, or lambda equals 1, or lambda 1 equals 1.5 in the slow region, then what is the wavelength, or what is wavelength 2 in the fast region? That's what they're asking us for here. Now, if I was to draw a wavefront diagram very quickly to represent what's happening here, here's how I would do this. So I would create one section that has very tight lines together, representing that this would be something with a small wavelength. And then after a couple lines, maybe I just extend these out and I draw where they have a larger wavelength. Now, based on the context of this, we want to write an arrow that represents which direction the motion is going or which direction this wave is actually heading. If we know that the lambda is from crest to crest or trough to trough, what I'm going to do is I'm just going to put in a dot and say that this represents our lambda 1. And then for the second piece, when we start to see it increase to this region where we have larger wavelengths, I just want you to put from crest to crest that this represents wavelength 2. Now, based on the description of this, they said it goes from the region with a slow speed or a low wavelength to something with a greater wavelength with a faster speed, meaning when I draw my wavefront diagram, you need to draw the arrow heading this way or heading in the south direction, just based on orientation. Not saying this is like the way you have to draw it. You could even have drawn this left to right, but I just drew it up and down to save some space here. The arrow would be heading down or towards the faster region here. And that would be the direction of the wave's energy or motion. Now, let's use that identity from the previous page that was established. And so I'm going to go back and just remind us of what we have on our formula sheet. It's the following: V1 over V2 equals lambda 1 over lambda 2. Let's write that out and let's see if we can solve this. So I'm going to go V1 divided by V2 is equal to lambda 1 over lambda 2. Now, solving this, again, we're trying to solve for this lambda 2. I can use this mathematical property where if I do the reciprocal on both sides, this maintains the ratio for us and allows us to then put the lambda 2 to the numerator. And it reverses both sides. So this is going to be lambda 2 over lambda 1. Now, the only thing we need to do algebraically to isolate for that v, or lambda 2, I should say, not v2, but lambda 2, is multiply the lambda from the denominator. And this is going to give us lambda 2, which is equal to the speed 2 times lambda 1 divided by the speed of the first wave. Now, plugging in all the numbers here, lambda 2 is equal to the speed in the second region was 60 meters per second. The speed in the lambda in the first region was 1.5 meters. And then the speed in the first region was that 45 meters per second. Okay, now when we do the math here, let's make sure we can get a specific number here. I'm even going to pull out the calculator just to make sure we get everything correct here. And so when I type this into the calculator, if I do my 60 times the 1.5, and then I divide it by 45, I end up getting a wavelength of 2. So my lambda 2 is equal to, and just to keep significant digits, I'm going to make this into 2.0. Now, here's a way I could extend this problem. Not saying they asked anything about it in this case, but when I look at this, what they could have done is they could have been like, well, what if I asked you for the frequency of the wave? And the correct answer you should be thinking about, just even besides the algebra, is to get the correct answer for this in terms of frequency, we could use either wave. And the reason we can do that is because we know the frequency, regardless of the region, is the same. So let's say we're in the slow region, the frequency is the same as the faster region here. So now our job, if we wanted to do just kind of like an extra piece, I'm even going to phrase it like that. I'm going to be like, if we're talking about some sort of extra extension to this problem, not saying it was asked, what I can use is the universal wave equation, frequency times wavelength equals the speed. I can isolate this for frequency, which is equal to the speed over the wavelength. And now I just get to choose either one I want. Do I want to deal with the fast region or do I want to deal with the slow region? And maybe I'll just plug in both here to show you that it does actually equal. Frequency 1 is equal to V1, which the speed in 1 was 45 meters per second, divided by the 1.5 meters, which represented the wavelength. In the second region, we said that the V over lambda was equal to 60 meters per second, divided by the wavelength, which we actually just solved for, which is 2 meters. This is equal to frequency number 2. What we're going to find is that this value is equal to, for this one, 30 meters per second, or more importantly, 30 hertz, not meters per second. This is a frequency, so it is measured in hertz. And then in terms of the other value, this is also equal to 30 hertz, meaning our frequencies are equal. So we could have extended to this problem. If they ever ask you for frequency, just pick one region or the other and know that your frequency is determined by the source. It doesn't change even when going from one medium to the other. Therefore, you can get it either way using this information. All right, now we're pushing into the idea of diffraction. Diffraction, again, there's not a ton of this in Physics 20 necessarily. The biggest thing we need to pull out from here is that diffraction is this concept of waves that want to bend or spread as they go around different corners or obstacles, and this is what we call that diffraction. Now, the way I like to explain it using the two examples below or using these situations below is that we look at the following here. So suppose that I have some sort of wave and it's heading south because we see this arrow representing the direction of the motion. It's heading down like this. Now, as it heads down, it's getting essentially it's guided by this wall here. But as soon as the wall breaks, then the wave energy is now free to move past that region. And the way I like to draw this here and what diffraction is doing is that once it breaks past that wall, now it's trying to disperse. It's trying to like figure out and trying to fill this empty space continuing on. So we would see that we could draw on all these arrows representing that it's going along. The origin was somewhere up here. It generated this wave. The wave heads south. But once that guiding wall breaks, it's now going to want to space out and fill out the empty space. Now, we look at an example like this, and from class, I even said, I was like, if we have a situation where a wave is heading towards a door, something like my voice and the sound of my voice is going this way, the waves that are being generated by my voice as I teach my lesson, it's going to break through the door. But we're going to look at this and be like, well, some of this wave energy will get reflected. So it might even just come back this way, come back this way. It might just get reflected within the class here. Not all of this energy is going to make it through, but of the energy that makes it through, we're going to see that it spaces out. And so we start to see this filling of the empty space or filling of this open area, and it's going to want to space out or disperse. And this is what we call this concept of diffraction. Now, I asked you this case scenario. I said, well, what would happen if, let's say I'm talking at a certain volume and then I'm trying to ask you about a question of how long would you hear me for? Like, would my sound waves just carry through the door and then infinitely extend through the school? And for many of you, you just say clearly, no, that doesn't make sense. Your voice will only go so far. And the reason is because the energy that's within this wave or the energy that's being generated from this isn't going to go in perpetuity. It's not like it just continuously seeks out more and more open space. We're going to see that eventually this sound energy has been dampened so much by external forces or external particles or whatever it might be. It's getting dampened along the way. It's losing more energy. It can only disperse so far before all of that energy has been dispersed and you'll no longer hear me. So if I'm in one end of the building, you're not going to hear me on the very far side unless I have like some megaphone that can really amplify my sound. But we're not going to see that there's enough energy within my regular talking voice to carry this and diffract all the way around. Now, again, we're going to see more about this in Physics 30. There's a ton of content regarding this in Physics 30. So for now, this is as much as we need to know is just the general principle, because then you can start talking about this later on. And again, this is the phenomenon that explains why sound waves can easily bend around a corner, or as they travel through a door, we see this principle exactly acting out. Okay, now interference. We've talked about this in lesson 26 quite a bit, so this isn't going to be anything super new to us. But when we talk about this, the one thing you can annotate here is interference is this idea that we get waves that are interacting with each other and or interfering. Now, that could either be a positive interference, which we sometimes call constructive interference, or not sometimes, but we do call that. And then in terms of destructive interference, it's these areas where they're kind of playing this tug of war against each other. It's like who has the greater positive or negative amplitude, and that determines the overall result. So we look at this piece here and we're going to put a dot here in the middle and a dot here in the middle. And off to the side, I'm just going to indicate that these represent the sources, or these are the sources of the wave. And from the sources of the wave, we start to see these interference patterns in which they're continuously interfering with one another. And we get this constructive interference, destructive, and it just continuously and successively continues this pattern as long as there's energy in these waves outwards and outwards and outwards. So this striping pattern, as we can see, destructive interference is going to be all those darker regions or those black regions. And then when we look at the constructive interference, it's all these areas of white. Now, again, constructive interference is when you have two amplitudes that are both the same orientation heading towards each other and they constructively build together. Now, that could be in the negative direction, such as building a trough. It could be in the positive direction as building a crest. But we look at it and say there are two waves same orientation of amplitude, whether positive or negative, heading towards each other. Destructive is the opposite. We have some orientation heading one towards each other. We have the opposite orientation. So one orientation could be positive, the other one could be negative, heading towards each other, and they're going to act against each other in kind of a tug of war scenario. And then the resultant will be the product or the addition of those two. Maybe not so much the product, but the addition of those two, the sum of those. Now, to help us represent this with even more specific terminology and maybe a diagram that will help us out a little more with this, when we look at waves that constructively interfere, these are those areas which we call antinodes or maxima. When we look at destructive regions, these ones are going to be called nodes or minima. Now, the naming, and it's like of an antinode or a maxima, these are those areas in which we get the largest buildup from the equilibrium point. And so if I highlight these on in my notes here, this constructive interference area, they're actually really easy to identify. It's these areas in which you see overlap of the two lines or the two energy regions. And so you would see, if these are diagrams of waves, specifically these could be wavefront diagrams for how they're represented, we look at this and say, those dark lines are crests. And if we're meeting crest to crest, it must be that we're getting these areas of buildup, or we're getting these areas in which they're constructively being added together. In the case of destructive interference, we look at this and we say, well, it must be these areas in which a crest would meet a trough or vice versa. And that's all those areas in which you only see white space with a line going through, white space, a line going through, white space, a line going through, white space, a line going through. And so this pattern could continue to the left or to the right. As long as this constructive and destructive pattern continues to go on, or as long as these waves are propagating outwards, you're going to see that this pattern continues to some extent. Now, again, we want to look at this and be like, these two at the bottom here, or these two dots, just like in our previous diagram, these represents the sources of the wave. So I would always just indicate that here and just say, this is the given source. Perfect. Now, again, just as because I don't know if I did a good enough job with the nodes and antinodes comment here. Antinode, you can think about it as it's going against the equilibrium. It's trying to displace itself from the equilibrium. So it's anti-equilibrium. It's anti-meeting at that equilibrium point, anti-node, or a maxima. When we look at destructive interference, it is called a node or a minima. It's a minimum displacement from the equilibrium position. Because remember, it's all in relation to that equilibrium position, the equilibrium being, if there was absolutely no energy in this wave, well, I don't even know if we would call it a wave at that point. A non-energetic wave would just be something that is stationary water, let's say. So there's no ripples, it's just sitting calmly with no sort of energy being propagated outwards to different points. Okay, now we go into this idea of what happens when we deal with path interference, and specifically two waves that meet either constructively or destructively. So we're just taking that and looking at it a little closer. Now, in the case of this section here in the notes, I want you to write that this represents source 1, or the first source. This represents source 2. Now, these are some distance apart, but then they're heading towards each other in a way that eventually they'll overlap. And what I would like you to do on the endpoint here is just put a point like, maybe they meet right about here. We're going to call this point P. And the number one thing you're going to notice is that when these things meet constructively, you notice that their overlap becomes perfect in the sense that they meet crest to crest or trough to trough. And that would become as they meet, or let's say they only meet momentarily, because they don't always have to meet in perpetuity, or as they meet, they don't have to like join up and synchronize together past that point. They could just temporarily meet at that point P and then disperse away from each other again. But in this case, I just want to say, hey, they meet at point P. The pattern we start to notice is all these areas which their troughs meet, their crests meet, their troughs meet, their crests meet, and eventually they'll perfectly overlap if this is a path difference in which it's an integer value. And here's what I mean by that. Suppose that I have source 1, which is this shorter wavelength, and then I have S2, which has that extra wavelength or extra lambda on it. As long as that extra lambda is just an extra lambda, and it's not something like a 0.5 or a 0.75 of a wavelength, these things will end up meeting perfectly in a sense that they will constructively work together. We see that if I label this as point P, that meeting point of the two sources, again, we're seeing that pattern where trough to trough, crest to crest, trough to trough, they constructively meet or constructively interfere with each other. Now, looping in some math terminology here, Again, as long as it's a multiple of lambda, or what we're going to call n lambda, this means that n has to be a multiple where it's an integer value. Sometimes we could even say n would be an element of the whole numbers. That might be even a little more specific, saying that n has to be a multiple of, is it that the path difference or the difference between source 1 and source 2, is it a whole number wavelength? Is it one wavelength? Is it maybe two wavelengths? Is it three wavelengths? As long as it's this integer value or that whole number difference, we can say that this will perfectly constructively interfere. And the example I used in class, just to make this very, very specific, is I said, what if I started clapping and a second later you join in with the exact same rhythm? Well, the frequency is the same for both of us, but I've started one clap ahead of you. The wavelength is the same because the distance between my two claps is the same, and the distance between your two claps is the same. So let's say that I start that one clap ahead of you, or maybe even two claps ahead of you. Then, even if I start that two claps ahead of you, we'll meet constructively because then we'll all join in synchronous together and we'll all be clapping at the same frequency and wavelength. And we'll be clapping in a way that it adds up together, or they build each other together. Whereas we look at the opposite situation, which says that if I have destructive interference, we get this idea that it's either a rational or irrational number that is forming the difference in wavelength. So if source 1 is going and then we add a source 2, when they meet each other, because they're a half lambda different, or we could even say like something like 3 over 4 or 3 over 2 or 5 over 2, these rational or irrational values that aren't perfect whole or integer numbers, it leads to this idea in which when the waves meet each other, you're going to have this idea of they're working against each other. We don't get this nice pattern of crest to crest, trough to trough. In fact, at point P, which I could label somewhere here, or even somewhere towards the end, you see this situation in which a maxima is meeting a minimum, and then, or a crest is meeting a trough. And then again, a crest is meeting a trough. And we don't want this. In any sort of constructive situation, they should be meeting together, crest to crest, trough to trough. So how I always like to phrase this one here is mathematically, I say it's n lambda, where n is an element of either the rationals or the irrational numbers. So something like, you can even say, as an example of an irrational number, it's a pi length difference, 3.14, ugly number, but it's an ugly number difference. We could also say something like in the examples below or above, sorry, 3 over 2 is an example of a rational number, but it gives us 1.5. We don't want 1.5 as a number. That's 1.5 difference is not good. And here's what I will explain and how I explained it in class. When we talk about S1 and S2, let's say I'm S2 and I start clapping. But then between my claps, you're clapping and the rest of the class is clapping. That means that we're going to have this constant pattern of us alternating. When you clap, I'm not clapping. When I clap, you clap. And then it's like that's not adding together. That's not making this nice, beautiful, synchronous sound. It's we're working against each other. We're playing tug of war against each other. That's the way I like to sometimes describe destructive interference. It's a constant like tug of war against the two waves, and you're working against each other rather than working together. Okay. Now, as we move into the next part here, this is just an example of how this could look algebraically in terms of how do we know destructive or constructive based on the wavelength length or the total segment length. So in this example, what they do is they give us source 1 and source 2, and they say when these waves meet at point P, will they be constructive or destructive based on the wavelengths? So right away, I'm going to write is if PS, or line segment PS1, is equal to 80 centimeters, let's write that in here. Then the other line segment, S2P or PS2, is 90 centimeters. Ideally, we don't want to work in centimeters, but what they did is they gave us the wavelengths in the given centimeters, so we can use this to our advantage. You only necessarily have to convert if they're in different units, but for all of Physics 20, we've tried to remain pretty consistent to meters. So if you wanted to convert these to meters so that you can use them, good. Otherwise, if you realize that it's centimeters and they're both centimeters, that's okay. Now, to solve this and to explain if it's destructive or constructive, we're going to start off with the idea that what if both of them share this idea that they both have wavelengths of 5 centimeters and their line segments are described by this. To solve this algebraically, we're going to go below and we're going to do this first case in blue, 80 centimeters divided by 5 centimeters. This gives us a total of 16 wavelengths, or 16 lambda. When we do the same thing, but for the second line segment, 90 centimeters divided by 5 centimeters, we end up getting that this is representative of 18 lambda. Now, the number one thing I want you to notice here is what is the difference in pattern? This is the way I write it, difference between the two. 2 lambda. And if the difference is 2 lambda, that means this is an integer value or a whole number difference. So this is like me starting 2 claps ahead of you and then everybody in the class joining together with the same wavelength and same overall pattern, the same amount of claps. So we look at this and say, even though I may get a head start on you, I'm only 2 claps ahead of you and I'm an even 2 claps ahead of you. So by the time that we reach point P, or by the time we reach that distance, we would be synchronized together constructively. So therefore, this is constructive. And I'll just short form it as constructive int. Okay, now if we do the other situation where instead of it being 5 centimeter wavelengths, what if it's 20 centimeter wavelengths over these given distances from S1 to P and S2 to P? Well, the math would look the same, except we're just dividing by 20 instead. So 80 divided by 20 centimeters, this is going to give us an even 4 pi, or 4 pi, I shouldn't say 4 pi, 4 lambda. And then 90 centimeters, which is our second line segment, divided by 20 centimeters, this is going to give us a value of 4.5 lambda. Number one thing you should notice, what is the difference in the path length? The difference in this path length is a difference of 0.5. So we're going to write difference is 0.5, and more specifically 0.5 wavelengths. And if the difference is 0.5 wavelengths, therefore this is destructive. And again, I'll just short form the interference as int. So this would be an example of I clap and then you clap in the space between my claps, and then I clap and then you clap in the space between my claps. It's not a nice situation. We don't like it. So we're just going to write this as this is destructive. We're working against each other. This is counterintuitive, or it's not necessarily counterintuitive, but it's counteractive to what we're trying to build, which would be more constructive. We want to add the crests and add the troughs together, or add our claps and then leave the white space for white space rather than having a clap in between those two things. Okay, moving into standing waves. Standing waves are this concept in which we used to go through these in depth, and in Physics 20, it used to be a very big topic. In fact, it almost could be a lesson in and of itself. But in terms of standing waves, we just need to know the general premise and the general terminology. And then on the next page, what I'm going to actually do is just draw out an example of a standing wave. And then I'm going to challenge you to try your own as well, which is exactly what we did in class. So when we talk about standing waves, it's this idea in which what happens when we have a situation where we have two waves with the same amplitude and the same wavelength traveling towards each other. Well, what this generates is this idea of an interference pattern called a standing wave, or a wave that appears to remain constant in its position. Now, the result is nice because then it gives us this ability to determine nodes and antinodes, or points of maxima or minima, as we call them, very, very easily. And so this is a really nice pattern for this. And so on the next page here, if we know that these standing waves appear to remain consistent and then they lead to these areas of predictable nodes and antinodes, or maxima and minima, then let's make sure we can draw out our own example using what I like to call, or what is called, harmonics. So in class, what we did is the following. I want you to just draw some sort of box like this that is a rectangle with an open top. So it should look exactly like that. And then what I want you to do is draw an equilibrium point down the middle. Now, in class, what we dealt with is the following situation. What if I draw the wave that is like this, and then like this, and then it comes back up, and then it's paused? Okay, so this is the one wave, or the direction of the wave. The wave was going left to right. It's heading left to right following this given situation. Now, on the backward situation, we have this idea that we have a wave that is going down, and then it is going up, and then it is going down, and then it is going up. We get a wave that looks exactly like the following. Now, if this was a perfect depiction of this, we would have that our maximum, our crests would all be in line with each other, and the troughs would all be in line with each other. So in fact, what I'm going to do is just fix this one a little bit because this one seems to be the biggest issue. Just make sure that it follows along this bottom line and then cuts back up there. So although this still isn't perfect, it does the trick. Now, this is going to introduce a standing wave in which represents a certain n harmonic. So in order to determine what harmonic this is, I think we need to fill in the important information first and foremost from our unit here. So right away, we want to fill in the nodes. The nodes are the areas in which the standing wave is on the equilibrium. So that appears here, it appears here, it appears here, it appears here. So there is 4 positions of what we call nodes, or these ideas that if we even flip back here, we're going to go back to our slide here. These nodes are these areas of minima. So we're going to use both those pieces of terminology side by side. Nodes or minima. And I'm going to make sure I point to all of them here. So here, here, there is one here, and then there is one here. And then I'll just make sure I write up above all of them, nodes slash minima. There we go. Now it applies to all those black arrows. Now, if we've pointed out the nodes or minima, or the areas in which the standing wave exists on the equilibrium point, and it's these predictable patterns, remember, again, you should be able to directly see them from this visual, which in this case we do. The other areas, which we call antinodes or maxima, are those other regions in which they're furthest apart from the equilibrium. So using, let's say like the pink line here, I'm going to point to these areas here, 1, 2, and 3. These are those areas of what we call antinodes or antinodes slash maxima. Now, again, when we look at this standing wave here, this is this concept in which we see that this predictable pattern of waves with the same amplitude and wavelength are heading towards each other. They create this pattern, and this would be something that would be happening in perpetuity. We want to get a little more specific on the terminology here. The antinode or maxima determine the harmonic. So to label this below here, I'm going to write this as this is, and I'll switch back to my black pen here. So this is going to represent the nth harmonic. The antinodes or maxima determine whatever harmonic it is. In our depiction of this, we have a third harmonic situation, or a third harmonic standing wave. Okay. Now, if this is all the terminology we need to know, specifically the nodes, minima, the antinodes, the maxima, and then how we determine the harmonic, which is determined by the amount of antinodes, we can draw whatever harmonic we want. In fact, what I'm going to challenge you to do on your own, and I won't cover this in this video, but I did this in class. I just said, make up a number. It could be the 7th harmonic. It could be the 6th harmonic. It could be, in the example that I asked in class, what is the 5th harmonic standing wave? This was what I challenged you to do. I definitely recommend you try this on your own. So what would the 5th harmonic look like? And then label all the depictions of this piece here. Okay, very, very important. You should be able to replicate this. You should be able to do this, but that's as much as we're going to do with this idea of standing waves, which account for, again, by definition, 2 waves with the same amplitude and wavelength heading towards each other. Okay. Now, we shift into this idea of what we call natural frequency or resonant frequencies. And that's this idea of when we look at natural or resonant frequencies, every object, no matter what it is, has a natural or resonant frequency. And through that natural or resonant frequency, what we can identify or what we can see is that objects with the same natural resonant and frequency will vibrate at a certain tone or will transmit energy together. And so when we look at this idea of every object having this natural or resonant frequency that it will vibrate at, if we look at this, it's saying that an object won't vibrate at any other rate than that given frequency. So in class, what we did is we set up this pendulum situation here, and we had B and D and A and C, and I said, okay, well, which ones are going to vibrate together if I produce some sort of energy? And I'm just going to use some mathematical numbers here to help us out. So suppose that some energy is transmitted down the line, or some given frequency is inputted down the line. Now I'm going to give a specific one. suppose I say that 10 hertz is implemented down the line, and I'm going to say that B and D have a natural or resonant frequency of 10 hertz. And then let's say this one has a natural or resonant frequency of 20 hertz, and that's for A and C. Well, hopefully, correctly, you would say, oh, the one that's going to vibrate, given that this line has a frequency given to it or an energetic situation that lines up to a frequency of 10 hertz, is going to vibrate B and D because they match to that natural or resonant frequency. When we look at, if I change this number at the top here and I make this maybe, let's just make up a number of like 30. If I make this 30 hertz, well, then I could ask you, what would this vibrate at if the line was emitting this 30 hertz? You would say nothing because 10 and 20, those aren't 30. And if it isn't 10 or 20, then this isn't going to vibrate. Nothing would vibrate. Lastly, I could say, what happens if we made this 20 hertz? Well, 20 hertz going down this line would clearly match up with our bottom two, or A and C. These ones would vibrate together because they share that same natural or resonant frequency, or that same energy required, that natural vibratory energy that we're looking for. So it won't vibrate anything other than that. It's this specific frequency for a specific object. All right. Now, again, this natural phenomena of objects that are able to, almost like, you could think about it as like they're communicating with one another, or that they resonate to the same thing. When they resonate to that same frequency, this is called resonance. And this behavior of resonance is, if I have resonance, it's that there's a certain frequency that's being emitted, that frequency matches up to the object, and then we get this repeated situation of oscillation where the energy is being transmitted. You see that this frequency is matching up, and then this can actually lead to things that are of natural disasters. And so when we look at this piece here, this idea of resonance or natural frequencies or natural resonance that lines up, why is this important? Well, if every object or every mechanical system has the ability to absorb vibrational energy from a surrounding frequency being given off, this can lead to things like resonant disasters. Resonant disasters, we're going to play a couple of those videos in class, and maybe I'll even link one or two of them in the section below or in the bio of this video. A resonant disaster occurs when something like in the video I'm going to show, wind picks up, and wind is having this certain frequency or this certain vibrational energy. This vibrational energy is then passed on to the bridge. The bridge matches up to that natural resonant frequency, and then we see that the bridge will start to sway, or it will start to gain energy, because that resonance property or this ability of the bridge to absorb that natural vibratory energy will then pick up, and it will amplify. And when it amplifies, eventually it leads to the bridge collapse. And then so we propose the following question: how do we prevent that sort of a disaster, or how do we prevent this resonant disaster? We use what we call damping. And damping is a process. You just remove some of that oscillatory energy, or you dissipate, or you try to disperse that energy as much as possible. So in the example in class, what we did is we took two tuning forks and we put them, let's say like a meter apart from one another. And we played around with the distance a bit, but we took tuning forks and they had 440 hertz. And so I'll even just draw like a rough picture of what this kind of looked like in class. So I'm going to draw the box that held the tuning fork. The tuning fork then went up from the stand like this, and then had its forks go up like this. And then we saw that another tuning fork was over here. And I'm going to try to draw them as best as possible. They should look pretty much the same. This will do the trick though. Now, what I did in the experiment, or what I did, is I hit this side with a mallet with a rubber ball on the end. And what that did is that emitted a frequency, or it emitted the natural frequency of the tuning fork that was 440 hertz. And that 440 hertz was symbolic of an A in like the music terminology. So if we want to describe like what note we emitted, it was an A, and it was 440 hertz. Well, 440 hertz was also over here. This tuning fork is also a 440 hertz tuning fork, meaning its natural or resonant frequency is also 440. And so what happened is that vibratory energy was heading towards the fork, heads towards the fork, heads towards the fork. And what we ended up seeing is that you could actually hear that fork as well at that A pitch. Now, given it was much quieter because not all of the vibratory energy or not all of that energy is being transmitted to this given tuning fork. It's getting transmitted to the surrounding area. So only a little bit is reaching that tuning fork, but the little bit that reached that tuning fork matched that natural resonant frequency. It vibrated the tuning fork, giving off this A, and therefore we were able to see that objects that share this same resonant or natural frequency will vibrate together given that that energy is given off. Now, where the damping process came in is in the case of damping, once I hit this with the rubber mallet, I covered this with my hand. I covered up the tuning fork, I grabbed it. And when I grabbed the tuning fork, all of you noticed that the sound then just cut off. We couldn't hear the sound anymore. And it's because when you dampen or when you dissipate or remove energy from the system, you are no longer hearing that emitted 440 hertz with that energy. It's being dissipated to your hand. The energy has been removed by some sort of external force. Now, in really tall buildings, when you talk about damping, there's a couple really cool examples where we talk about damping in buildings where there's these counterweights or counter pendulums that prevent from huge sways due to either earthquakes, tsunamis, or some sort of shift in the building. They prevent against the building collapsing, especially for these really tall buildings. Having a counterweight is really important to make sure that sways do not pick up or a resonant frequency is not matched by some sort of external force, which could then lead to the building swaying and then breaking apart. We don't want that. So what I would say is the video that I'm going to include in the denominator, I'm thinking about my math terminology. The video that I'm going to include in the bio of this video is the Tacoma Bridge. The Tacoma Bridge is a really good example of seeing how the wind, which had a certain frequency, can then transmit that energy or that vibrational energy to the bridge, which match that natural frequency, and then the bridge sways, and eventually collapses. All right, this is where you're going to want to get your practice problems done. We're officially done the waves section of Physics 20. We have one more lesson after this, but it is very important to go back through lesson 26 and 27 and build mastery around all this terminology that's being thrown at you.